All right, I think everything is up and going now. Hello, everybody. Mr. Barden here. You might not be seeing, or I know you're not seeing me on the screen. If you've watched any videos on this channel, you know I tend to show up in the kind of bottom right corner of the screen. I've just recently replaced a bunch of bulbs in my living room where I do this, so it's I've just got to adjust some light levels because these new ones are a lot different than my old bulbs, and everything looks really, really blown out in the color. So I'll get to that at some point. Okay, I'm just going to jump right into it. This video is an introduction to the audio unit of the Programming Digital Media course. Uh, Assuming I have time, I am going to go through and make several videos about a lot of stuff you can do with this platform. The videos about tone tend to be the better ones on my channel, just in terms of people watching and learning stuff from them. So again, if you do enjoy this video or you learn something useful, go ahead and give it a like or subscribe and blah 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 YouTube stuff. You get the deal. All right, so if you look in the description of this video, you'll see a link to this page right here. This is the beginning of the Sounds with Tone.js section of this course. There's a lot of stuff, just basically this opening page is how to include the tone library in your JavaScript sketch. I may get into some coding here. I put a link to this sketch, but at the moment, again, I do these kind of live and semi-improvised, so I don't know if we'll be jumping into code in this video, but we'll see. I do know if we do, I'll come back to this, but it's relatively straightforward. If you've watched my videos with P5 Play, it's the same idea, but with a slightly different setup if you are using the P5 library. Anyways, if you head over to the next page in this section, this just kind of briefly goes over, or semi-briefly, it's kind of a long page, but a lot of the ideas of sound. And basically, I'm just going to kind of go through this just to provide as many people as possible with a just kind of general background for how does sound work, and then how do computers work with sound, so that way we can hopefully have a good foundation for everything that we're going to be doing over the next few videos to come out. So just starting right at the top, actually I do want to say, just because I see an image down here, I do not own any of the images used here. If I have the top, whoever made this, I put it in this page for that, but I did not make any of the images myself, with the exception of this table. Okay, so sound is what happens when one thing essentially vibrates and bounces into another. That may seem a little weird considering we hear sound just about everywhere in most cases. But basically, when something vibrates against something else, those vibrations will transfer from A to B to A to B from whatever made the sound until it hits your ears or a microphone or something perceives that. We will see a diagram in just a moment that kind of illustrates this a little more clearly. But if you wanted to kind of feel this, you can take your hand and put it kind of up against your throat. Don't choke yourself for the sake of this, but you can kind of, loosely but firmly kind of just place it around your throat and then start talking at a, decent-ish level. I mean, you don't want to whisper because then you won't be able to feel it. So if you talk a little bit louder, you should be able to feel the vibrations in your vocal cords as you are talking. These vibrations travel at different rates through, different materials. So generally, when we think of sound, we're hearing this through air. But as the materials get denser, I could have sworn steel is denser than aluminum, so I'll have to double check that. But anyways, generally, these are approximate, but as the denser the material, the closer the molecules are in that material. So that way the energy can travel faster because the molecules don't have to vibrate as far in order to bump into the next one. That's why in space, where there's essentially nothing in a vacuum, the there's nothing to vibrate, so sound can transfer. Generally, in air, the speed of sound is 331 meters per second, or approximately 1,000 feet per second. Again, I'm speaking in approximates here. Um, so let's look at this diagram right here that I think will help illustrate this. So let's say you have something is making a noise. Like, so we've hit one thing has hit another, and it's causing this these air molecules around it to vibrate. Where you're going to notice that the air molecules tend to kind of clump up together and then bounce apart from each other, and this forms these repeating waves of high and low air pressure. So again, you'll when someone talks about waves or the frequency of waves, they're talking about the physical air getting more compressed as the molecules are vibrating and they're bumping up against the ones next to them. But then if you've ever thrown a ball against a wall or seen uh, something bounce a little bit when you drop it, you know that things tend to bounce off of each other, so the molecules kind of bunch up and bounce off. And these movements are a lot smaller than these diagrams might make you think, because again, we're talking molecules, but they've just been kind of blown up for the sake of the diagram. Uh, so again, we have high air pressure, low air pressure, and so on. And we'll generally see these waves of pressure traveling out in all directions from the sound source. If you ever see this kind of diagram here, it's called a waveform diagram. And when the line goes high, that's indicating high pressure at that particular time. As it goes down, that's low pressure at that particular time, and so on. You may have seen this before just when looking at a lot of sound files or graphics of audio, but they tend to be a lot more zoomed out. Again, these are traveling very fast, so there's a lot of variations in a waveform diagram. All right, so here's, again, the frequency. So at this point, we've discussed that audio kind of travels in these waves of high and low pressure from whatever's making the sound to whatever is perceiving the sound. The times per second that these waves of pressure are hitting our ears tell us, what pitch it is. So something that's a really low pitch, like ooh, and something that's a very high pitch, like ooh, are going to have a very different amount of frequencies hitting your ear per second. Or I'm sorry, a very different amount of waves hitting that. I have a link to a video here by the YouTube channel admin of this site. There we go. They aren't an admin of this particular site, but anyways, I've got this right here, and this, I'm not going to play it because copyrights and stuff, but basically this just takes a sine wave and it does a full signal sweep, essentially starting at 20 hertz and ending at 20,000 hertz. So to explain this, hertz is a measurement, essentially just meaning times per second that something happens. All right, so the times per second that we are hearing these waves of pressure hit our ear, we measure that in hertz. The lowest ish that people can hear is right around 20 hertz, with the highest of that range being right about 20,000. So this can vary from bit to bit as we go along. So as you age, depending on the sound itself, things like that. Sorry, you can't see it, but my cat decided she wanted to start destroying everything on my desk here. That's the one downside of not having a camera. Sorry about that pause. Hold on, someone is just spamming my chat as I do this. One second. Boop. I'm just clearing off the spam. Okay. Wonderful. Okay. Sorry about that. Got horribly distracted by cats and spam on my chat here. Um, where was I? Oh, yes. Depending on things like the shape of your ears, your age, the distance you are, and the volume of the sound, there's a whole bunch of factors. So this that can affect the range of your hearing in terms of frequency. But generally speaking, 20 to 20,000 hertz is, approximately what a human can hear at their, peak level. Generally, once you start going past about 17 or 18, you'll notice that that high end starts to decrease. Everyone's different. I'm trying to speak as generally as possible, but if you play this video here, I'm curious to see where you might hear things start and stop. Um, Again, I'm not going to do it here, but I am curious. So if you do it, put that in the comments. It could be fun. Don't spam it like the person or the bot probably just did on mine. But anyways, one final note: if you do listen to this, though, if you have a nice pair of speakers that are pretty big, that's probably a better thing. So you'll hear the higher and lower frequencies. I don't recommend hearing it with headphones because it can get a little bit piercing and not fun if it's at a fairly high volume. Okay. Next thing, perceived pitch. So right here, I have a piano with all of the notes marked. So basically, if you see this, then within an octave, on the standard convention is to start each octave and go from C all the way to B. But you'll notice that it's repeating in this kind of cyclical pattern, using the white keys C, D, E, F, G, A, B, C, D, E, F, G, A, B, C, D, E, F, G, A, B, and so on. The number is designating what octave we are. So C2 is one octave below C3, which is one below C4 and 5, and then so on. Essentially what's happening here, if I scroll down to the next diagram, we can see the frequency of these notes compared to the notes on the keyboard. And again, just the really short version is that every time the frequency doubles, we are moving up an octave. So this is a logarithmic growth. So down here on the low end of the piano, looking at the A's here, 27.5 hertz, that is A0. But if we jump up to A1, that is 55 hertz, if I'm reading that right. It's a little cramped. But then A2 would be 110, A3 is 220, A4 is 440, 880, and so on. So we have to, essentially double every time we want to move up the octave. Yeah, here is that math again. So this is true of any note, not just the ones on the keyboard. Again, keyboards play a very specific set of notes, but you can effectively play any sound in between these just by specifying a specific amount of hertz for a synthesizer to play. We'll get to that. That's not one of these amounts. So if you double it, it'll be an octave higher. If you have it, it will be an octave lower, and you can work out ratios to get other intervals with that. Okay, I'm not going to get too much into this diagram, but generally, if you were to go back to this video, which again, I highly recommend you listen to on your own, you may notice that the volume seems to change. Just like, we can hear different frequencies throughout our life, we can also hear different volumes of those frequencies. This may change, and again, it has a lot of the same factors as perceiving the frequency, but generally, over here on this graph, I can make it a little, I didn't make it much bigger. This is the volume, the perceived volume of a sound as the frequency goes up. So we can hear a fair bit of low end noises, a lot of those loud sound effects, super bassy stuff we can hear really well. And then the volume kind of tickles down, and then we start to get this interesting kind of peaks up again as we go. So this will live, I need to replace this with a bigger image, but generally around 2000 hertz And then again at 8,000, we tend to notice a spike in what we can hear. These are approximately some if we wanted to get into the whole evolution things, speaking, singing voices, baby crying, stuff like that, we get little bumps at the important aspects. That's what's important here, just from a general evolutionary standpoint. But what's important to know is that if you're ever mixing the volumes of your sound, you may have to bump certain frequencies and lower others to make it all sound flat. So this is just a general outline, and again, the volume of the sound that you're listening to itself can affect this. Just know that volume perception can change with the frequency. When we're talking about volume, a lot of times we're essentially talking about amplitude. I have this diagram again. So we've already discussed that the frequency is the number of times that this wave is hitting your ear and your eardrums per second. What we haven't discussed is the size of the waves. And essentially, a louder volumed sound has a larger amount of waves, more energy in it, that's hitting our ears. So I'm going to do a demo of this with the microphone. So I'm just warning you now, if you're listening to this on headphones, in just a second, I'm going to make a loud noise. Okay, this is going to be my second thing. The first bit is going to be really, really quiet, which is why I warned you before. So, because I'm being quiet, what's happening is I am not pushing as much air with my vocal cords. All right, the waves themselves are very small. In just a moment, I'm going to talk loud now. As I'm talking kind of loud, the vocal cords are pushing more and more sound with each vibration. Again, the waves themselves are bigger, so more air is being displaced. I'm getting a little distortion as I'm talking this loud. But again, as we're pushing more air, it's moving things more and more in our ears, in the air, so it just sounds louder. I'm not going to go through all of the math, but here's some math just kind of illustrating that a little bit more. Okay, so I'm at more or less a normal volume now. We measure this in decibels, all right? And decibel can be a confusing kind of way to measure things because it can be used for different things, but generally we're describing the sound pressure level. All right, that's what SPL stands for up here. And we'll talk about ears in just a moment, as if you see down there. But generally, as we're talking, we're creating these bits of air pressure, and having too much pressure can be a problem. In the human ear, there is a membrane that kind of breaks up the inner and outer ear, and if it hits too much pressure, you can break that, which is a problem. So I'm not going to go through it in detail, but here you can kind of see some general levels of sound. So again, the higher on the scale, the more damage you could have, and it's color-coded to be very useful. But keep in mind that, again, even the lower volumes can be problematic if you're exposed to them for a very long time. Again, I'm not going to go into detail, but this should hopefully give you an idea of different sound levels, and that yes, very loud things can hurt your ears. That's why I warned you that I was going to make a loud noise a bit earlier. Okay, there's this diagram one more time. We've talked about, this volume, frequency, but now we're going to talk about the ear. Don't worry, in a little bit we'll talk about the speaker, but now we're talking about the ear. So I have this diagram here from Encyclopedia Britannica, just going through, what is an ear. So here we have the sound coming into our ear, and the outside here, this is essentially called the pinna, is the whole thing. But this serves as kind of like a satellite dish. And what this will do is, again, funnel the sounds into your ear, and they're going to travel into your head through this little canal until it hits the tympanic membrane. And this is, if you've ever heard of someone refer to the eardrum, that's what this is. This is essentially just a little membrane right here that's going to take in the sound, and that's going to cause this to vibrate. These vibrations are then channeled through a few different bones. We've got 3 of them here, until they hit the cochlea. And I'll show it in a second, but this is kind of a wrapped up little organ right here, that's filled with a bunch of fluid and, for the sake of getting too much into it, little hairs, or hair-like things. And essentially, higher frequencies will vibrate, things down further on this, the ones down on this end. Lower frequencies can vibrate the ones closer to the beginning, and so on. And as these vibrate, they stimulate different nerves that then go to our brain. And this is what lets us be able to tell different sound frequencies. And again, louder volume, more stimulation, so our brains can respond to it, and the brain is what's interpreting everything else. Again, if I were to pull this up here, again, we can see that this is, again, a very, very blown up bit of the cochlea. It's kind of wrapped up really tightly, but as we're, actually I had that backwards, but certain frequencies here are responding, and as we go down, they tend to get filtered out, until we get, again, really low frequencies or stimulating sounds down here. So you can see that, this is all getting stimulated, this isn't, as we go along. All right, so that's just a really brief oversimplification, but we don't need to get too much into it. Okay, I'm going to talk just a little bit about microphones, because while for this class we won't be recording anything, it's important to know that, for any sound file playback, someone had to record or create something in order for us to play it back. So microphones. I'm not going to go through too much, but there's generally 3 common kinds. There's a dynamic microphone, and this is just a coil wrapped around a magnet. As those sound waves from whatever that's recording hits this little diaphragm, it pushes the coil around the magnet, and that generates electricity, which then goes out the wires to whatever we've plugged it into. A condenser microphone is a little bit different. It's running an electrical circuit here, and as those sound waves hit the diaphragm, it's going to push 2 metal plates closer together, and they'll move farther apart. Again, these are very, very small movements. As it gets closer, it changes the electrical resistance, which then changes the electricity amount going out to whatever we've plugged it into. Ribbon microphones function essentially the same way as the cochlea, where different frequencies cause different parts of a metal ribbon to vibrate. Again, I'm very, very simplifying this, but we don't need to go too much into detail. These essentially function as an electronic ear. All right, their goal is to take the sound waves coming in and convert it into electricity for our computer to use. In order for a computer to record the signal, again, this is specific to computers, we have to do a little bit of interesting stuff. So computers, if you weren't aware, work in what's called the digital realm. They use, discrete numbers, ones and zeros, to represent things. Electricity does not have ones and zeros. It is just, electricity. So there's, in most computers, there's something called the analog to digital converter, which can let us take in audio sounds and convert that into a digital file. If your computer has a microphone of any kind, it has this already built in. Otherwise, you can get these that plug into the computer. So you can plug a microphone into the box and then into the computer, so on and so forth. But essentially what these are doing is it's taking this voltage that's being input from the microphone, and it's essentially taking a snapshot of that voltage at a given point in time. So I've got this diagram here. Again, that doesn't get any bigger. I don't know why that's a feature on this web page, but I didn't make that part. So generally, every sample is this little black dot right here. You can see the general curve of the actual sound, and then the kind of squared off bits of the digital bit that we've recreated. So every certain amount of time, we take a snapshot of the audio and record its given level at that instant. The general standard for this is 44,100 times per second. That is very fast. Go away. The reason for this, I'm not going to get into all the physics behind it, but generally you want something that's at least twice the range of hearing, so that way we don't get any weird artifacts and things, because again, you notice that this is a lot more blocky than the original sound, and that just helps eliminate the blah, blah, blah. But just know that 44,100, that's the important thing there. A lot of, quit doing that, a lot of high def things, higher definition recordings, movies, films can have higher audio recording frequencies, but this does increase the size of the audio file. Remember, if you had a 60-second audio clip, it would be 44,100 numbers versus 96,000 numbers. So again, we can adjust the size. The other side of this is the bit depth. And it's very closely related. Again, more bits can make a bigger file and all that. But it's essentially, as we're taking a snapshot of these samples, we have to give it a discrete value. Because again, we're replicating this audio as closely as we can. So if here's the input, and we have, in this case, three bits of options here. Versus 4, 5, and 6, the more bits we have, the more essentially little categories we can put the audio level into, the more accurate our recordings get. So again, you can see down here at 3 bits versus 6 bits, this is much more closely replicating the actual input signal. That's why if you've ever used a bit crusher effect, it's reducing that bit noise, and it gets a lot more noisy and distorted because it's not accurately recreating this. The standard is more or less 16 bits at this point, but this can be higher, just like the sample rate. Okay, so what I want to talk about now, as we're getting towards the end, is just audio pathways. So I've mentioned that sound travels in waves from the sound source to whatever. So we have to replicate this continuous stream of information whenever we're working with sound. So in order to replicate this, I like to think of this again as a literal stream moving from A to B. As we'll find as we go through more of these videos, we're going to essentially route the audio. So we're going to take the audio information, these numbers representing the recording that we've made or the signal that we've generated, and we're going to send it from, the file to an effect to some other thing, from A to B to C to D, all the way out until we eventually send it to the speakers. So again, it's a continuous stream of information. And because it's all numbers, we can change them up, and that's kind of the basis for audio effects. I'm not going to get too much into that right now because there's a whole section on audio effects. Once the audio eventually gets to the speaker, it functions essentially like a dynamic microphone in reverse. So the audio signal is going to come in through this cable, and it's wrapped around, this cable's wrapped around a magnet. As the, I'm sorry, we actually skipped a step. Before it gets to the speaker, we go through the digital to analog converter, which is the opposite of the analog to digital converter. It takes the numbers and changes it into an output electrical signal that we then transmit down the wire, and it goes up to the speaker. This wire is wrapped around a magnet, so as the electricity changes, it's going to move back and forth, just like before where moving it generated electricity. Again, everything's reversed. And then it's all connected to a big membrane. And then that membrane is what is pushing the air, so then we can hear things coming out of the speakers. If you have some computer speakers, you can try playing a sound and then just lightly putting your hand onto the speaker cone, vaguely cone-shaped, or the part where the sound comes out of, and you should be able to hear or feel these vibrations. If not, that's okay, but that is one thing you can do. Never like really manhandle those. They're relatively delicate. You just want to keep them safe. One other thing you can do if you don't have speakers, if you have headphones, you could touch it up with something magnetic, and you'll feel that magnet try to respond to other magnets. Okay, I'm not going to play this again because it's copyrighted, but this is from the Slow-Mo guys. And just to illustrate this, they've put paint onto a speaker, and they're playing it in very slow motion. But as the speaker moves back and forth, pushing the air so we can hear it, by putting something on there, we can see that relationship. So check that out. It's kind of fun. I won't play it in this video. That's a problem. I need to fix that. We're gonna look at that in just a moment. But if I don't open it up now, I'm gonna forget. Okay, so basically sound synthesis. So part of this course is going to be on playing back sounds. We've generally gone through that. We'll get into more detail later. The other half is generating the sounds for other people to use. So because this is all just numbers in the computer's mind, we can generate a pattern of numbers that continually happens from whenever we start it to wherever we start it in order to create sounds. This particular pattern, we have 4 basic ones, and they all sound generally different. This initially was going to illustrate all of those, but I'll have to replace that video at some point. But if you look at a sine wave, it's kind of a gradual curve between the high and low, and that is the pure sound there. Square waves tend to jump immediately from high to low with no slope, and we get all of these have different overtones. So they color the sound in different ways. A triangle wave is like a sine wave, but it moves directly from A to B with no curves. And then a sawtooth is kind of a combination of triangle and square, where it moves linearly or in a straight line from one to the other and then jumps back down. That's essentially that. The 2 different kinds of synthesis that we tend to use are additive, where you create complex sounds by combining a bunch of these small ones or adding a bunch of sounds together, versus subtractive, where we start off with a complex sound and we remove certain aspects we don't want in order to create the sound that we do. And again, I'll go through that in a little more detail when we get into synthesizers. As we're getting into the end of it, this is the last thing here. The envelope of the sound, the ADSR, you may hear it referred to as. This is the attack, decay, sustain, and release. Essentially, every sound has this envelope, and this is referring to the amplitude, the volume of the sound over time. Generally, with a synthesizer, or just the computer making audio, it is going to just output this stream of numbers forever. It's just going to go. We can alter the volume of this sound to give it whatever characteristic we want. And then generally we have an attack to give it all the main energy, and we kind of fall down, and then the sound will sustain for however long it's going and gradually release. So again, we increase the sound from nothing, a little bit of a slight decrease in volume. Notice it's much smaller than this. We sustain for the main bit and fade. By combining this envelope with these different sound wave synthesis methods, you have essentially endless possibilities for sound creation. To wrap this up, I'm just going to illustrate a few different envelopes using my wonderful singing voice. So with a really slow attack and release kind of thing, we can get kind of a again, we'll pretend the pitches didn't change. But again, a really long ramp in sustain and release versus like a that purposely was as short as I could physically make it. But a much shorter percussive sounds have, very fast, well, really everything, but almost no sustain, really intense attacks, and usually very quick releases. Um, so again, that's just kind of some two general extremes. I'll pretend that my singing example was any good. All right, that's going to wrap it up for this video. I hope this was helpful. Sorry about those distractions halfway through. Again, cat and spam bots. Anyways, I'm going to be wrapping it up for now. I ended up not using any code, so I'm just going to go back and remove that from the description right there. And yeah, we'll wrap it up here. If you enjoyed the video, feel free to give, like, subscribe, comment, all this stuff, YouTube, blah, blah, blah. It does help out. And I'm going to see you all the next time that I see you.